Okay, so hello everyone. So we are going to study about the subject digital design and computer organization from the 2022 scheme VTU. So according to the syllabus copy, we have in the first module, our first very topic is binary logic. So binary logic, if you see here, it is a big definition though, but still you don't have to worry about the definition because it's very simple and very easy. So basically, right, binary means two, just two. So in digital design, we'll be having like binary means we'll be talking about zeros and ones. So here, first just let me read the expression. Binary logic consists of binary variables and a set of logical operations. The variables are designated by letters of the alphabet such as A, B, C, D, W, X, Y, Z, etc. with each variable having two and only two possible distinct values, that is 1 and 0. So we talked about the variables, and there are three basic logical operations, and or not. So you all would have studied this in your PUC level education. So let me just show you here. So what they have said, binary logic consists of binary variables and set of logical operations. Suppose there is any like variables, they say, right, x, y, z, a, b, c. So suppose you would have come across some operation, logic operation. This dot is for and, this is and, this is or, and this getting a bar on that any particular letter, suppose a bar. So that is not. So these are the variables and these are the operations. Okay. So if you talk about like suppose a plus b, or let us take a plus a bar is equals to yeah. So if you take a plus a bar is equals to a itself here again. So how we got a here, we will be discussing that later, but just an example to show that it is a consists of variables and set of variables and operations. So just this expression you have to write in the terms, that's it. You have to write this expression in words. So that will be your binary logic. And see, suppose if they have asked for just few marks definition and this two separately, if you write, it's enough, more than enough. Suppose they have asked this for more mark because it's the first topic, right? So nothing, you just have to explain this each logic gate, AND gate, OR gate, NOT gate. For AND, this is the logic symbol. For OR, we use this, and for NOT, it's like this. Just write separately for each AND, OR, and NOT. Draw the truth table. Use any two variables, and for result, you can use another variable and display that. So here you can, as you have seen here in the bracket, explain each gate if asked for more marks. So this is the first topic here. Moving to next, we have some binary theorems, like binary logical, so binary theorems here in this chapter. Coming to that, we have, you can see here, you have 6 theorems and the postulates, which means here, see they have mentioned here postulates, right, 1, 5, and again here postulate 3, postulate 4 and all. So that you don't have to prove, okay. That's just like in maths how we say we know that from this, that, like that. So here you don't have to prove this, but theorem you have to prove here, okay. So first theorem we have here, x plus x is equals to x, and x into x is also equals to x. So you have to prove this first. So how we are going to prove? I'll be solving that now itself. So you see theorem 2, then you have theorem 4, here theorem 3 over here, theorem 4, 5 and 6. It's not that difficult, it's very easy, and we will be seeing that now itself. So here before we move on to that theorem part, so I just want to explain you about this logic gate, some set of rules. So as you can see here, for NOT gate just does one function, which is give the complement of the function. Complement is nothing but this bar over here. So what does the NOT gate do? Suppose this is a NOT gate and we are passing a variable, suppose a. So our output, in the output, let us keep the output as y result, y is equals to a bar. If we give b, y equals to b bar. So what it is doing is just giving the complement. Suppose we had another logic like 2 NOT gates here, okay. So here if you pass A, here y equals to A bar over, and again here y equals to A double bar. Now this A double bar is again equals to A. How I will be saying that now. So let us give a value for A, okay. We know either it can be either 0 or 1. Suppose A equals to 1. So what will be the complement of A bar? It will be 0 obviously. Now if A equals to 0, what will be the complement of A bar now? It will be 1. So see here, from this if I take A double bar, okay, A equals to 1, A bar is 0. So A double bar is equals to complement of 0, right. So what is the complement of 0? Which is again 1. So same here, A equals to 0, A bar equals to 1. So here A double bar will be equals to complement of 1, which is equals to 0. Understood? I will write it again neatly. So A equals to 1, then A bar equals to 0, then A double bar equals to 1, which is nothing but A double bar equals to A itself. Moving to the AND gate. So I have draw this truth table over here, A, B. Here first is for the AND gate and second is for the OR gate. Okay, so I will just draw here the AND gate. This is AND, this is OR. Okay. So see here, we have taken 4 conditions over here, and in each condition first we have multiplied A with A itself, A with 0, A with 1, and then A with A bar. So in each condition we will be taking, if A equals to 0, what will be the result of the above, if A equals to 1, what will be the result of the above. So see here, we have taken A into A. If A equals to 0, so both the place 0 will be substituted. 0 into 0 is 0. It is just as your simple mathematical calculation, okay. Anything into 0 is 0, and yeah, so if it is 1 into 1, same into same, 1 into 1 itself is 1, remaining all the gates will be 0. So see here the logic gate, 0 into 0 is 0, 0 into 1 0, 1 into 1 is also 0, only 1 into 1 is 1, okay, remaining all are 0 here. So we won't be seeing that. Here if you see now, A into A is equals, so if A is 0, 0 into 0 is 0, and if A equals to 1, 1 into 1 equals to 1. So what does this say means, A into A is always A. So no matter what value of A you are giving, in the output side we are getting the same value. So input, what input you are giving for A, the output is same. Coming to second condition, A into 0. If A is 0 here, so we will just substitute the value of A in this A place, that is it. So 0 into 0 is 0, and if you put the value of 1, A equals to 1, 1 into 0 is again 0. So from this you can say that A into 0 is always 0, or else just you can see here, anything with 0 is always 0, right. So A into 0 directly you can write as 0 itself. Coming to third condition, A into 1. So we will take if A equals 0 or A equal to 1. So just substitute the value of A in the place of A. 0 into 1 is 0, again 1 into 1 is 1. So here again you can see whatever the input you are giving, that same is reflecting in the output side. So here you can write as A into 1 is equals to A. Therefore, and coming to the last condition, if A into A bar, means A into A complement. So here if you take A equals to 0, so 0 into 0 complement, which is nothing but 0 into 1, which is again 0, and if you take A equals to 1, 1 into 1 complement is nothing but 1 into 0, which is again 0. So again you can write that A into A bar is always 0. So you have two conditions over here, A into 0 and A into A bar is always 0. So both are this 2 and 2 and 4 are always 0, and coming to 1 and 3 they are always equals to A itself. This is this was about the AND gate, and let us see about the OR gate. So it adds the two binary variables. So A, B. These are the two inputs given to this logic gate. In the output side, you got y equals to A plus B. So what is the logic in this? Like if there is one higher input, then the output is that higher input itself. In the sense, if you have one in either of the variables inputs, then your output will automatically be 1 itself, the higher value itself. So see here, so same conditions we have taken, here we multiplied, here we will add, because here it is OR gate. So see here A plus A. Now in the place of A we will substitute 0 and 1. So if A equals to 0, 0 plus 0 is 0, and if a equals to 1, 1 plus 1 equals to 1. So you can see here a plus a is always a. So what input you are giving, the same output you are getting. Coming to the second condition, a plus 0. If a is 0, 0 plus 0 is 0. If a is 1, 1 plus 0 is 1. Again here a plus 1 is equals to a itself again. So whatever value of a you are giving the input is equals to, it is same reflecting in the output. So see, if you compare here a into 0 was 0, but here a into a plus 0 was a. So here please don't go by hearting these things, just try to understand. If you don't understand anything, just go behind reverse and just again try to listen to that explanation again, you will understand easily. If you understand, then you don't have to by heart itself, aram se from your own explanation you can write this. So third condition, a plus 1. So if a equals to 0, so see here 0 plus 1, if you have one higher input, then the output is higher itself. So when 0 plus 1 is 1, and if a goes to 1, 1 plus 1 is 1. So here you won't write a plus 1 is equals to a, don't get confused. Here you will write a plus 1 is equals to 1, because no matter what input you are giving, the output is 1 itself. So here inputs are different, but output is same. So a plus 1 is equals to 1. Coming to a plus a bar. So it's very easy. So if a equals to 0, always say a complement 0 complement 1. If a equals to 1, 1 complement will be 0. So no matter what, in both the case you will be having either one will be higher. So obviously the output will be 1 itself. So again don't go and write a here, a plus a bar equals to 1 itself. So this was a small like explanation with a set of rules which was required for us to solve these theorems. So before solving theorems, this all conditions and this explanation will be helpful for us. So now let us see this theorem list again. So we have here theorem 1 to 6. So we will be solving each part one by one. So it's not that difficult. If you solve one, the another is easy itself.